We've been told that digital sound is a staircase, a crude approximation of reality. But that staircase is a lie. In 1948, Claude Shannon published a mathematical promise that sounded like a magic trick. He claimed you could take a smooth, infinitely detailed sound, like a violin solo, shred it into a few thousand pieces, throw most of them away, and later reconstruct the original perfectly. Not mostly perfect, a reconstruction so exact there's physically no difference between the original and the copy. We assume the space between digital steps is a blind spot where reality vanishes. But today, we're going to prove that the staircase is a lie. In the physical world, a sound wave is continuous. It has a value at every infinitesimal moment in time. This feels like it should be infinitely complex, but Claude Shannon looked at a sound wave and saw it as just another vector, only this time, the vector lives in a space with infinite dimensions. To store this infinite wave in a computer, we have to find a coordinate system for it. We do this by taking snapshots or samples. Imagine a strobe light flashing in a dark room. You don't see the continuous movement of a dancer. You only see where they are at the exact moment the light hits. Each flash is a sample. Intuitively, we think that the more flashes we have, the better the quality. We imagine a sliding scale where 1,000 flashes is good and 1,000,000 flashes is better. There isn't a sliding scale. There is a boundary, a hard limit where the staircase suddenly, mathematically disappears. To find that boundary, we have to look at what happens when we fail. Imagine a wave that is vibrating very quickly. Let's say it completes one full cycle every second. Now, suppose our sampling camera is lazy. It only clicks once every second. If the camera clicks exactly when the wave hits its peak, every single sample we record will be the same number. To the computer, this fast, energetic wave looks like a flat deadline. The information hasn't just been simplified, it has been disguised. This is the wagon wheel effect. You've seen it in movies where a car wheel appears to spin backward even though the car is moving forward. The wheel hasn't changed. Your sampling rate, the camera's frame rate, is just too slow to keep up with reality. In engineering, we call this aliasing. It is a masquerade where a high-frequency signal pretends to be a low-frequency signal. And here is the terrifying part. Once a signal aliases, it is indistinguishable from the truth. No algorithm and no amount of enhancement can ever tell them apart. They have collapsed into the same set of numbers. So, how do we stop the masquerade? The answer is the Nyquist rate. You must sample at least twice as fast as the highest frequency in your signal. But why 2? To understand that, we have to leave the world of time and enter the frequency domain. Just like we can break an arrow into X and Y coordinates, we can break any complex sound into its frequency ingredients. A pure sine wave is just a single sharp spike on a frequency chart. Now, here's the secret. Mathematically, the act of sampling creates shadows. When you take discrete snapshots of a wave, you aren't just recording that one frequency spike. You are inadvertently creating an infinite hallway of mirrors. In the frequency domain, your original signal is suddenly surrounded by identical shadow copies of itself, repeating forever. If you sample very quickly, these shadows are spaced far apart. But if you slow down your sampling rate, the shadows creep toward the original signal. The moment your rate drops below the Nyquist limit, the moment it's less than twice the highest frequency, the shadows overlap. They bleed into each other. This overlap is aliasing. Once the colors bleed together in the frequency domain, they are mixed forever. You need twice the frequency because you need enough space for the original signal and its shadow to sit back to back without touching. Now we come back to the staircase. If we have sampled at the correct rate, how do we get the smooth wave back? Most people think the computer just connects the dots with straight lines, but that's not what happens. To get a perfect reconstruction, we use a mathematical tool called a sinc function. Imagine every single sample point isn't just a dot, but the center of a beautiful, rippling wave that spreads out in both directions. When you add all these rippling waves together, a miracle occurs. The ripples cancel each other out in the gaps and reinforce each other on the peaks. The jagged staircase vanishes, and the original, smooth, continuous wave reemerges. This is the ultimate payoff of the sampling theorem. It tells us that a smooth world isn't infinitely complex. If a system has a speed limit, a maximum frequency, then it is actually finite. It can be fully described by a simple list of numbers. But there is a catch, a mathematical tax that nature demands in exchange for this perfect reconstruction. Look closely at that sinc function, the golden ripple. It doesn't just spread out, mathematically, it spreads out forever. To perfectly reconstruct a single note played a second ago, the computer technically needs to know every sample that will be taken until the end of time. This is the pre-echo paradox. In a perfect mathematical world, digital audio requires future knowledge. But since your computer isn't a time machine, we have to cheat. We use a filter. Think of it as a brick wall in the frequency domain. It's a physical gatekeeper that says, nothing faster than this is allowed to enter. This is why, when you look at a digital file, the staircase isn't the problem. The speed limit is the reality. Claude Shannon didn't just give us a way to record music. He proved that reality itself has a resolution. He showed us that infinite detail is often just an illusion, and that as long as we know the speed limit of a system, we can capture its entire soul in a string of ones and zeros. But there is one final ghost in the machine. Even if we've proven that the timing of digital isn't a staircase, what about the volume? When we take a sample, we have to round the wave's height to the nearest available number. This is quantization. If the timing is the horizontal axis of our reality, quantization is the vertical. This is where the staircase myth actually comes from. If you only have 4 levels to describe a sunset, you get ugly bands of color. If you only have a few bits to describe a violin, you get a harsh, grainy hiss known as quantization noise. But Shannon and his successors had one more trick up their sleeves: dither. It sounds counterintuitive, but to make the digital world perfectly smooth, we add a tiny microscopic amount of random noise before we record. This noise acts like a mathematical lubricant. It breaks up the rigid, predictable steps of the staircase. By adding this dither, we can actually hear sounds that are quieter than the smallest possible bit. We've traded a jagged, artificial distortion for a natural, flat floor of silence. We haven't just captured the wave. We've ensured that even the parts we had to round off still carry the breath and soul of the original performance.